Thank you, Gustavo, for the introduction, and thank you for the invitation. It's a pleasure to be here. So yes, I will be talking about breeding dairy cattle to improve milk quality. So let me start with this question, right? What's the goal of a breeding program, right? Remember, farming is not a hobby. Farming is for profit. So the goal of a breeding program is either to improve the traits that increase the revenues of the farm, or improve the trait that reduce the expenses of the farm. So when we think about traits that increase the revenues, we think about mostly production and product quality. And when we think about the trait that reduce the expenses, we think about fertility, health, calvinability, and even efficiency. Now, I think this is an important question for this audience, right? How important is genetic selection? And I will try to answer this question, showing the change in milk production per cow per lactation in this country. So I'm showing here, this is data from Holstein. The change in milk production per cow per lactation in the last 60 years. It's easy to see that there has been a tremendous increase in milk production per cow per lactation. In fact, the cow today, she produces more than twice as much milk as the cow of 60 years ago. And 60% of that change is due to genetic selection. In fact, genetic selection is a very powerful tool to achieve lasting gains in dairy cattle performance. And contrary to changes that we can achieve through nutrition, through management, through cow comfort, the changes that we achieve through genetic selection have three unique features. They are cumulative, they are permanent, and they are incremental. They are cumulative, they are permanent, and they are incremental. And that makes genetic selection a very cost-effective strategy. Now, these are the traits that we have under selection in this country. As you see, we are selecting for production, including milk, protein, fat, and milking speed. This is the most recent trait, and is particularly a good trait for this audience. We are selecting for cow fertility. We are selecting for cow longevity. I will be talking about longevity later, but that includes productive life and cow mortality, and we also include now heifer mortality. We are selecting for health. I will mention that in the next slide. We select for calvinability, conformation, and we are also selecting for feed efficiency, including residual feed intake and feed safe. Again, the latest trait that was included in the National Genetic Evaluation was milking speed, and that's a nice trait for this audience. Now, when we think about health trait, when we think about other health and milk quality, we think about somatic cell score and mastitis. Somatic cell score was developed and implemented as a trait in 1994. As you know, it's based on somatic cell count, and somatic cell score reflects basically the genetic ability of a cow for other health. And then in 2018, we develop and implement 6 postpartum disorders. These traits are defined as disease resistance. Basically cows' genetic ability to resist to a given disorder. And as you can see here, one of these 6 postpartum disorders is mastitis. So for today, we have somatic cell score since 1994, 31 years ago, and we have mastitis, clinical mastitis, that is I would say a recent trait with 7 years under direct selection. Okay, so what we have here is what I call the genetic trend for somatic cell score. I'm plotting the change in the genetic merit of the animals in the last 40 years. This is for the Holstein population. And as you can see here, I have in red the change in the genetic merit of the cows, and I have in blue the change in the genetic merit of the sires. This is somatic cell score. Remember, somatic cell score measures the genetic susceptibility of the animals, so lower values are better. As you can see, the genetic susceptibility of the Holstein population increased until 2000, 2005, and since then we have observed an increase, if you will, in the genetic resistance of both sires and cows. Remember again, negative values, lower values are better in this case. And as you see, what you expect, there is always a gap between the sire population and the cow population because of selection intensity. We tend to go faster in the bulls than in the cows. And here I'm showing the genetic trend for clinical mastitis. Remember, clinical mastitis is measured as the genetic resistance of the animal. So in this case, positive values, larger values are better. Easy to see that until, 2010, 2015, the genetic trend for clinical mastitis for both cows and bulls, they has been quite flat, but we have observed a quite important increase in the genetic resistance of both sires and cows in the last, I would say, 10, 15 years. And again, as we expect, there is always a gap between the sire population and the cow population. We need to go faster in terms of genetic improvement at the bull level than at the cow level. Now, we don't select animals for one or few traits. If we do that, we will be doing a mistake. The best selection tool that we have is to use an index, an economic selection index. Let me repeat again the same. Farming is not a hobby. Farming is for profit. So the best way to identify the best animals is to actually use an index that will maximize the profit. And I'm showing here the current picture of the net merit index. You probably will agree with me. The net merit index is the flagship of our dairy industry. There are other indices generated by CDCB, three more: cheese merit, fluid merit, and grazing merit. We do not have a economic selection index for organic farms yet. And we also have indices generated by companies and breed associations. Now, if you see here the current picture of the net merit index, we have roughly almost 50% of the weight goes to production. We have roughly 20% that goes to health. And if we combine residual feed intake with body weight composite efficiency, this the ability to produce the same amount of milk using less feed, account for roughly 18% of the index. You see here, somatic cell score has a weight of almost 3% in the current version of the net merit index. It's negative because we tend to reduce the somatic cell score. Somatic cell score measures the genetic susceptibility of an animal. And then mastitis is within health and account for roughly 1.5% of the index. Now, I will mention later, but this is important. Longevity when you combine productive life and cow livability, account for almost 20% of the index. In US, we put a lot of emphasis on longevity. So this is a picture of the evolution of the net merit index. Until 1994, we had few indices. All of them uses only milk components. You see here, the first version of the net merit index was in 1994 with productive life and somatic cell score. And then you see clearly here some changes across the years. Some important changes was, for example, in 2003, when we include daughter pregnancy rate. Daughter pregnancy rate until today is the primary trait that we have to select for cow fertility. We include net merit residual feed intake in the net merit index in 2021. And then we have some update weights this year. So you see how the emphasis on selection has evolved in the last 50 years, from only production to today, where we select for fitness and production efficiency. This is a graph that it has already some years. I generate this plot for a book chapter a few years ago, where I tried to show economic selection indices for 13 different countries. You have here the countries here, and then you see the emphasis in colors, right? And as you see, every country select for production, but the emphasis is different, right? We have countries like Spain and US, where 45–50% of the index is for production, for productive trait. And then we have trait like the Nordic countries or the Netherlands, that they have a weight a bit lower, around 30%. The same for fertility, right? Every country select for fertility, but we have some examples. For example, Ireland, typically a grazing system, is a seasonal system where fertility is extremely important. As you see in Ireland, the fertility has a weight of roughly 20–25% of the index, while in other countries like Spain and US, the direct selection for fertility is kind of lower, is maybe between 5 and 10%. The same for health, direct health, right? The Scandinavian countries, they have been selecting for health for a very long time. In Nordic countries, for example, health as a trait that you can select directly has a weight of roughly 20%, while in other countries like US, health directly has a much lower emphasis, maybe 5%. What is quite unique about US and few other countries is the weight on longevity. In fact, longevity as a combination of productive life and cow mortality has an emphasis of almost 20% in US. And think about it. In order to have a cow that stay in the farm and be productive, she should be healthy and she should be fertile. So when we put a lot of emphasis on longevity, we are indirectly selecting for more healthy, more fertile animals. Now, of course, we are still in the latest revolution that I call the genomic selection, right? Genomic selection was implemented in this country in 2009, 2010. So we have right now 15–16 years of genomic selection. It's based on a very simple but elegant concept. Is the use of genetic markers across the genome to predict breeding values. If you use the genome of an individual to predict breeding values, then you can, using that method, you can select animals at a very early age, right? And that has a positive impact in whatever system you can imagine, in particular in dairy cattle, where all the relevant traits or the economically relevant traits are observed only on the females, and they are only measured until the females begin lactating. So if you can use a tool that is based on the DNA, now you can make selection decisions at a very early age. We are talking about birth or even at the embryo level, right? I have just one slide to show how genomic selection works. Imagine we need what we call a reference population. It's a population where we have phenotypes and genotypes. And then with that population, because we have phenotypes and genotypes, we can estimate the SNP effect on the phenotype, and with that, we develop a prediction equation. After we develop the prediction equation depends only on the genotypes. So if I'm in front of a newborn animal and I genotype that animal, now I can feed this prediction equation and I can predict the genetic merit of this individual. Of course, it's a prediction, so it has associated an accuracy that in dairy cattle we call or we name reliability. How accurate is that prediction? How reliable is that prediction depends on many factors, right? But probably the most important factor is the genetic connection between my candidate, this newborn heifer, and my reference population. In other words, if the prediction equation was developed using a Holstein population, and I'm trying to predict the genetic merit of a Holstein heifer, then my predictions will be very reliable. Now, if my prediction equation was developed with a Holstein population, but I'm trying to predict a Jersey heifer, there is a disconnection between my candidate and the reference population, so my predictions will be very unreliable. And of course, the predictions also depends on the heritability of the trait. Traits with higher heritability tend to have more reliable estimate than a trait with lower reliability. This is a picture of the US Holstein population we have right now. You see here December 2025, we have right now almost 10 million genotype animals in the national database. This is just to show you that this is a tool that is used by farmers routinely in this country. What is very interestingly is that the vast majority of the genotypes in the national database, they come from females. As you can see here, the males represent only a very small proportion of the genotypes in the national database. The vast majority of the phenotypes, they come from heifers. They come from heifers from commercial farms. Again, genomic testing is a tool widely used, routinely used by farmers in this country. This is, I promise, my only equation in the presentation today. This is how we calculate genetic gain per unit of time. Once again, we do farming and we do genetic selection, not as a hobby, but as for profit. So we want to actually maximize the genetic gain per unit of time. And as you can see here, how fast we can move forward, it depends only depends on four parameters: the reliability, the selection intensity, the genetic variance, and the generation interval. And the use of genomics, the use of genomic testing has a major impact in at least two of these parameters. One is on the reliability, that measures how accurate genetic merit and estimate. And of course, one of the beauties of the genomic selection, if we can estimate genetic merits in a more precise way. So this parameter increases with the use of genomics. And the other one is the generation interval, that is measure the time between generations. And in males in particular, genomic has reduced the generation interval significantly. If not, look at this. This is the change in net merit in the Holstein population in the last 25 years. I told you genomic selection was implemented in 2009. So as you can see here, the Holstein population in the pre-genomics era was a population under selection. We were moving forward, right? At a rate of basically $5-6 per year. Again, net merit is measured as dollars, so that's why the change or the average change per year is in dollars, right? During the implementation of the genomic selection, we actually accelerate the process to basically $38-40 per year. And as you see, in the last 15 years, when we have been fine-tuning that system and generating more and more genotypes, we are right now on with an average gain of roughly $88-90 per year. That means these Holstein bulls, they become better and better every year. That's why it's extremely important to use young genomic bulls and minimize or avoid completely the use of proven bulls. The goal is to use young genomic bulls. Of course, you don't want to use few of them. You want to use a pool of young genomic bulls, so you minimize the risk. We can discuss more about that in the during the questions. I told you genomics increases the reliability, right? And we think about reliability as how accurate genetic merits are estimated. So let's do the following exercise. We go to the maternity right now, and we are in front of a newborn heifer, and we need to estimate as precisely as possible the genetic merit of that newborn individual. If I don't have any other information, I will ask who is the sire of this individual, who is the dam, and then I will use what we call the parent average, right? That is the average of the parent. And believe me, if you don't have other information, that's your best prediction. Now, how accurate, how reliable is that prediction? Well, it ranges from 0, when you don't know who are the parents, or when you think you know who are the parents, but you are wrong. That means when there are problems in the pedigree, up to 0.35. Let's say if you have a very complete pedigree and you don't make mistakes. Now, if I tell the manager, give me 2 weeks, and you sample that newborn animal today and you genotype, now the selection decisions can be made based on the genome of that individual. And how accurate are the genomic breeding values of that newborn individuals? Well, it depends on the trait, but the reliability ranges from 0.65 to 0.80, right? A massive increase in how accurate are the estimation of the breeding values. And remember, reliability is in the numerator of my equation to calculate genetic gain. So if I have larger reliabilities, I will be able to move forward faster. So I will have larger annual genetic gains. This is a table based on the evaluation of December. I create this this morning. So we have data from more than 4,000 whole genomic bulls here. So I have different traits. As you can see here, I have production here. I have productive life here. As I have mastitis, that is quite important for this audience today. And I have here in yellow is the change in the reliabilities between what we call genomic testing and what we call traditional average, right? That is or parent average. Um, First conclusion, as you see, all the differences are positive and large. That means genomic selection has had a very positive impact in all the traits, production and fitness traits. Now, when you start to see the differences, in particular, you have a difference around 45, 46 for production, but then for longevity, you start to have difference between 49 and 53. For fertility, almost 50. And look at mastitis. Clinical mastitis has a difference of 51. That means the gains in reliability due to the use of genomic selection are greater for fitness traits. And when I'm thinking about fitness trait, I'm thinking about longevity, I'm thinking about fertility, I'm thinking about health traits. In other words, genomic selection has have a positive impact in all the traits. In fact, we have observed a twofold change in genetic gain for production trait, but we have observed changes between threefold and fourfold for the fitness trait since the implementation of genomic selection. Now, I'm pretty sure you in the audience are trying to answer this question, right? Does genomics work? Can genomic testing predict future performance, right? We have been discussing about genomic testing this newborn calf. Most of the farmers, they are genomic testing their heifers at weaning. Can genomic testing predict future performance? And for today, I'm bringing one example of production, one of fertility, and one of other health. This is data on roughly 1,000 cows. So I have basically 250 cows per bar. Here I'm trying to predict production using genomics. These cows were all genotype at weaning, right? When they had 60 days of age. We didn't use this information for selection of culling. So all the cows, all the animals, let's say, approach the first lactation. And in the first lactation of these individuals, we measure milk production. And as you can see here, the animals that at weaning, when these animals had only 60 days, we say these are the most productive individuals in the group, the top 25. These are the group that actually produce more milk. And the group that we say this is the bottom 25%, these are the worst individuals in terms of the genetic ability to produce milk. This is the group actually that produced the least amount of milk from this group. Beautiful result. Something similar for fertility. Here, the goal is try to predict reproductive performance using genomic testing. These animals were grouped based on DPR. Remember, DPR is our primary trait for cow fertility. Again, these animals were predicted when they have 60 days of age. We didn't do nothing. We just wait until the first lactation. And in the first lactation, we measure days open. As you can see here, the group of animals, that's 2 years ago, we say these are the most fertile animals based on their genome, is the group that showed the shortest days open, while the bottom 25%, these are the least fertile animals based on the genome, is the group that showed the longest days open. Another beautiful result. This is particularly interesting for this audience. Here I'm trying to predict other health using genomics. For that, I'm grouping the animals based on the genetic merit for somatic cell score. I have the top here and I have the bottom here. Once again, these animals were genotype at weaning. They have only 2 months of age. We wait until the first lactation, and in the first lactation, we measure somatic cell count. This is the average log of somatic cell count. Easy to see the group of animals that we say these are the most resistant animals, were the group of animals that show the lowest somatic cell count in the first lactation. The group of animals that we say these are the most susceptible animals, you know what, 2 years later, in the first lactation, this was the group that showed the largest somatic cell count in the first lactation. So let me revisit this question. Does genomics work? Can genomic testing predict future performance? I would say absolutely. Genomic testing can be effectively used to predict future performance. I haven't shown you, but as you can imagine, it's much more accurate than just using the sire PTAs, when we just try to rank the heifers based on the sires, we are missing two things. One, we are missing half of the genome that comes from the moms. And the second one, we are missing the Mendelian sampling. That is what actually brings variation when you think about full SIPs. The most important thing is, because we have a tool that can be used to predict future performance, we can use that tool to make proper selection decisions at a very early age, right? And what happened today is we have observed improvement in management, and we have been observed a lot of use of sex semen, so we have kind of a surplus of heifers. So we have room for selecting replacement heifers. How we can do it? Well, one way to do it is we can genotype all these heifers at weaning. We rank from the worst to the best, and we use different tools, right? We can use, in the worst, we can have early culling, or we can use beef semen if we want. And in the top, we can use sex semen, or we can have some of the very top heifers if we want to be more progressive and have a IVF program. This is a picture of the domestic semen sales in this country for year 2021, 2022, 2023, and 2024. Easy to see. There is a decrease in the use of dairy conventional semen in this country. I don't think this will stop soon. And at the same time, we see an increase in the use of both sex semen and the use of beef on dairy. And I like to say that the new club, the new group in the dairy industry right now is the use of genotyping to find the best and the worst, and the use of sex semen to replicate those best genomes, and the use of beef to avoid using those as parent of the next generation. This is a paper that we published 2 years ago, where we evaluate semen allocation in the Holstein population. We use quite a large data set, almost 5 million cows, almost 9 million inseminations. We evaluate 3 consecutive years, 2019, 2020, 2021. We group the cows in heifers, primiparous, second lactation, and older, and then we investigate different service numbers, right? And we wanted to basically better understand with this massive data set. Think about it. In this country, we have roughly 9 million dairy cows, and for this study, we evaluate almost 5 million semen allocation, right? And it's easy to see that we have observed a tremendous increase in the use of sex semen in the first service in the 3 years that we evaluate, mostly in heifers, but also in some first lactation cows. And at the same time, you observe a tremendous increase in the use of beef in these 3 consecutive years, mostly in lactating cows, but you start to see more and more beef semen also in heifers in later service, when we are talking about third service and later. Very similar picture when we talk about Jersey. Of course, we had access to a smaller data set, almost 300,000 cows and almost 500,000 inseminations, but very similar. the use of sex semen has increased tremendously in Jersey in heifers in these 3 years. And then you have a lot of semen used in lactating cows, in later services, but also you observe quite an important use of beef semen in heifers in third service. For those more progressive, you can use this idea of ranking your heifers using genomic testing and cherry pick the best one as donors. I'm showing here, this is data from actually farming in Spain, but it also applies to what happened in the US. When I was in Florida, I had access to the data from Don Benick from North Florida, Holstein, and I remember to observe exactly the same. When you combine the use of genomics to find the best donors, and you combine that with some advanced repro technologies like IVF, you can have remarkable genetic gains. Look at this. I have in 3 different traits here: fat, longevity, and a selection index. Longevity is, as you know, directly related with other health and milk quality. And I have it this farm. Something that is very cool in Spain that we don't do is in this country is you as a farm, you are compared with the province where your farm is and at the national level. And this farm has been using genomic testing to find the best donors and then IVF. And as you can see, regardless the trait, it could be fat, longevity, and selection index, this farm is moving forward in terms of genetic progress much more faster than the neighbors and actually the rest of the country. Again, when you combine genomic testing to find the best and you combine that with advanced repro technologies, you will achieve remarkable genetic gains. And it's very easy. If your animals are better in terms of the genetic merit, your animals will have a better performance. You will make more money. Another beauty of this genomics is the tracking of genetic disorders. Most of these known very, very bad recessive defects have been almost removed from the population. Now we are focusing in these haplotypes that affect fertility. These are regions of the genome that they have a sizable frequency in the population, but you never observe 2 individuals. You never observe an individual with 2 copies of this haplotype. That is a strong suggestion that if a zygote receives 2 copies of this haplotype, that fetus eventually will die. And here is a table of these recessive haplotypes. We have 9 or 10 haplotypes now in Holstein. We have at least 2 in Jersey and in other breeds. You can see for most of the haplotypes, we have identified now the gene that is causing the phenotype. Most of these haplotypes, when are discovered, they have a decent frequency. And here's the timing, is very important. Most of these haplotypes actually cause embryonic or fetal losses. All these haplotypes, they have a very negative impact on reproductive performance. And at the same time, with genomics, with genomic testing, we can track some of the milk proteins. So we can use genomic if we want to target beta-lactoglobulin or beta-casein with the A2A2 or kappa-casein. In other words, every time that you genotype a heifer, you can also have information about the genotype for these milk proteins, and you can target some of this in your breeding program. With that, I have some take-home messages. Genetic selection is a very powerful tool. I tried to show you that at the beginning of my presentation. The changes achieved through genetic selection are permanent, cumulative, and incremental. What makes genetic selection a very cost-effective strategy. Remember, we do not select animals for one of few traits, and if we do that, we are making a mistake. The best selection tool is to use economic selection index that try to maximize profit, and all these indices consider production, fertility, health, longevity, calvinability, and other traits. Something that is, I would say, quite unique of US is we have a lot of emphasis on longevity. Productive life and cow mortality together, they explain almost 20% of that, of the index. And remember, a cow to stay in the farm, you know better than me, she should be high producing animals, but also healthy and fertile. So when you select for longevity, you are indirectly selecting for more healthy animals, more fertile animals. Without discussion, genomics has transformed dairy cattle breeding, enabling faster genetic gains. Now, it's important to remember that the benefit of genomics is greater for low heritable traits, including health, including mastitis. And I didn't mention today, but genomics facilitate the selection for novel traits, right? For example, feed efficiency, or could be methane emissions, or could be other traits. We do have now the tools to actually select for traits that are extremely important, but are very difficult and very expensive to measure. Now, I show you data that genomic prediction can effectively predict future performance. That's why we can use the result of genomic testing to make early selection or culling decisions. The new perspective is to use the genotype of those individuals to fine-tune, to improve management selection decisions. And of course, there are extra benefits of genomic testing, including parentage verification, control of inbreeding, tracking genetic variants, tracking haplotypes that affect fertility, or tracking genetic variants that are related with milk composition, or maybe in the future with some fatty acid profiles, or some manufacturing properties. With that, thanks for your attention. Of course, again, Gustavo, thanks for the invitation, and I'm open for questions now.
Thank you very much, Francisco.